So in the previous lecture, we discussed how we generate electricity. Now we talked about the AC generator. So current, alternating current being created, being produced in a power plant. Now let's discuss how it gets to our house. Okay, so that's what this figure is trying to tell us. We had electricity generated down there in the power plant, for example, with a hydroelectric the water falling turned our loop, no, our turbine, and with that turn, the constant change in angle gave us this constant change in magnetic flux, which induced current, always in alternating directions. Okay, there we are. So our energy was produced. Now we have a certain amount of energy being produced, electrical energy in our case, per time. So this is, as we know, power. So the power of our power plant is given, no, we learned already about that. The power is given by I the current, and V, the potential difference. So this is the amount of energy per time, is the capacity of that power plant, and is giving us a certain current and a certain potential difference. Very well. What we are going to do before sending this current all the way to people's house is the following. Suppose that we generate our electricity, and in our drawing here, something around, let's just give it this as an example in this here, something around 12,000 volts, okay, and we have a certain current there. Okay, what we are going to do is we are going to use what is called a transformer, and you will see how it works next. In our case here, very close to the power plant, we are going to use a step-up transformer, which will increase this potential difference. Okay, so we are going to keep the same power, okay, but the transformer is going to increase our potential difference. For example, in this case here, they are saying that it's going to become 240,000 volts. Okay, so it was 12,000 volts, and now it's going to be 240,000 volts. Enormous potential difference. What is going to happen to our current? Well, our current is going to now become much smaller than before. Much smaller because this power is still the same. The amount of energy produced per time is the same. The only thing that we are doing is changing this potential difference. How we do that? By using a transformer. A transformer that increases the potential difference is known as a step-up transformer. And we'll see how it works next. And then you may wonder, okay, but why are we doing that? Well, this is a very important step. So we use this transformer. We now have a very huge potential difference and a tiny current. And this tiny current, we are going to let it travel over miles and miles, across cities, sometimes across states, all the way to people's house. And so we have this very small current traveling. And why? Because as it's traveling all these big distances, there'll be some losses. And the loss, so the power, now the power dissipated, the amount of energy being lost per time, not the one that was produced. The one that was produced is this part here that that is produced at the plant. What I'm talking about now, this dissipated power, is the energy, a little bit of the energy be lost as we travel these big distances. And this power dissipated is given by the current squared and the resistance along those lines. Okay, so the resistance is given by those long lines. I cannot change that much, but if I make the current very small, I will guarantee that the power dissipated is also small. Okay, so that's the purpose of doing this step up, of making this potential difference so large. Okay, but a potential difference this big is very, very dangerous. That's why you see as you're traveling, driving your car, on the road, you sometimes see these lines extremely high, to be safe. So it's very far from anyone. But once we get to the cities, once we get to our houses, well, handling those enormous potential differences is very dangerous. So what we are going to do, again, we are going to use a transformer, but now a transformer that is called the step down, that will bring the potential difference down to small numbers. So in this example here, we were traveling 240,000 volts. Now we go through this step down and bring the potential difference, well, in this example, to 2400. Okay, so this is a substation. And then we have, as it goes closer to the house, we have other step down transformers to bring it even lower. Now, so the potential difference that we have in our houses are 110 volts or 220, depending on the country. So much smaller than the enormous values that we had before. And so once we go through these step downs, what is changing? The potential difference is becoming smaller, and now the current is getting larger. Okay, but again, I repeat, traveling along those very large distances, we want the current to be very small, because this will guarantee that the energy dissipated through these wires will be also smaller. Okay, now I would like, so this is the general idea, but I would like us to watch these two videos that I am showing it here, because they are very interesting. I think he explains very well how the energy is produced and how it is distributed. So the first video is the one about producing the energy and talking about the step up transformer, and then the lower one is about the distribution. So let's start watching this first one. No, not this one. This first one about is the first video about the generation. Okay, so
Before electricity can arrive at your home to toast your bread, it has to be made first. Electricity is made or generated at power plants. Basic sources used to make electricity can be coal, water, natural gas, oil, nuclear, and wind. When electricity leaves the power plant, it is in its most powerful form, or as high as 765,000 volts. To compare, when it gets to your wall outlet, it is just 120 or 240 volts. From the power plant, transmission lines carry electricity long distances from city to city or from state to state. And these lines are held up and linked together by transmission towers, which are the big structures you have probably seen along the highways. These towers are usually about 100 feet tall and can be made of either metal or wood. Now, transmission lines are actually bare aluminum or copper wires, which are conductors for the electricity. Transmission wires are larger than the wires on poles in your neighborhood. Porcelain insulators hold the wires in place and keep the electricity running through the wires and not through the tower itself. And remember, a conductor allows for the easy flow of electricity, and an insulator protects or does not allow for the easy flow of electricity. In addition to the wires carrying the electricity, 1 or 2 ground wires protect the tower from lightning strikes. These bare wires are not safe to touch at any time. You should never touch, climb, or go near the towers or wires. Before electricity can travel from the transmission system and be delivered to your home, it has to make a stop at a substation like this. You've probably driven by a substation and not even realized what it is or what it does. A substation is enclosed by fencing for safety and houses the equipment that changes the electricity from one level to another. The electricity coming from the transmission line runs through a substation transformer, which transforms the electricity or steps it down to a lower level, reducing it from as much as 765,000 volts to less than 39,000 volts. This lower level of electricity is easier to handle and is now ready to be delivered to your home or business. But before we move on to the distribution system, let's now review some transmission system safety tips. Always assume wires have
okay, so keep going, watch the whole video, and well, and then he talks again a lot about security. He even says that some people steal copper wires, which is something very dangerous. But anyway, so again, let's compare with our video. he's talking about 700,000 volts because he's already thinking about the potential difference after the step up. And then he told us it travels through this um, um, very high transmission lines, and then it went through the substation. Now, in the next video, he's going to describe to us how this electricity now will get to our house. So he's going to talk about the poles that we see on the streets, and it's all, again, I think very interesting. So let's see.
After electricity has been made and transmitted to your city, it's time for it to be distributed to homes and businesses. The distribution system carries electricity at lower levels for shorter distances, such as from city to city or neighborhood to neighborhood. Like the transmission system, these smaller distribution wires are held up by distribution poles or buried underground. These poles are typically 50 feet high and are made mostly of wood. While the distribution poles and wires appear harmless, they must still be treated carefully and with safety in mind. Even the amount of electricity delivered to your home can cause serious injury if mishandled. Let's now explain what's on a typical distribution pole from the top to the bottom. At the top of the pole are the primary or main wires. These wires are coming from a nearby substation and can carry anywhere from 34,500 volts to 7,200 volts. The most common voltage is 12,000. Remember, the electricity started out as high as 765,000 volts coming from the power plant and was stepped down to lower voltages at substations. If the electricity is going to a home, there is typically just one main wire. If the electricity is going to a business, there would be 3 wires because a business usually needs and uses more electricity than a home. These primary or main wires are often held up on the pole by a crossarm. The wires are held in place by insulators, which help to keep the crossarm and pole from becoming energized by the wires. The next piece of equipment typically found on a distribution pole is a lightning arrestor. This is similar to a surge protector in your home. A lightning arrestor protects the pole's equipment from being harmed by lightning. At about the same level as the lightning arrestor is the cutout. A cutout is similar to a fuse in your home. It protects the pole and its equipment from too much electricity. If a squirrel or tree branch were to come in contact with a wire, the cutout will open, indicating a problem with that section of the line. If you ever see an open cutout, be sure to call your power company. Below the cutout is the piece of equipment that looks like a can. It is called a transformer. It takes the electricity from the wires at the top of the pole and steps it down to the lower level needed for a home or a business. Remember, wires can either be on a pole or buried underground. If the primary wires are underground, then the transformer is the green box often found in front, side, or backyards. So, if you have overhead lines, you will have a pole and transformer. If you have underground lines, you will have a green box on the ground. Now let's get back to the pole. Under the transformer is another copper wire called the neutral wire. This does not mean it is safe to touch. The neutral wire is a return line that goes back to the substation and helps to balance the amount of electricity out on the system. Without a neutral wire, our appliances could get too much or too little electricity, which can cause damage. In recent years, the rise in copper prices has made it a precious metal, and as a result, copper neutral wires like this have become a target for thieves. Copper theft is a huge risk to the thieves because they can be killed by coming in contact with a neutral wire. However, it's also a big risk to the public. Many times thieves will cut the wire and leave loose ends hanging where people and animals can come in contact with them. Below.
Okay, so watch again until the end, but I think you got the idea. No? So, see, he talks about, again, a lot about security, and he talks about the small transformers, no? This kind of transformers that we find closer to our houses, and also about how we can break the circuit in case of dangers. So that's the end, but watch the whole thing, and then we can discuss.